and we'll be looking at modeling with exponential functions in this section. We have looked at linear modeling, and we've also looked at quadratic modeling and even a little bit of modeling with higher order polynomials. So you're familiar with the idea that a mathematical model is a way to use an equation to represent a real-world situation, often based on certain data that you might have. When we're looking at exponential modeling, we'll of course be looking at our standard exponential function, ab to the x. And there are certain situations that can be modeled exactly with exponential functions. As we'll see, there are a lot of important applications that do fit a perfect exponential curve. Compound interest, things like medication in the bloodstream as it wears off, radioactive decay. Those are all perfect exponential functions. Let's start with a compound interest problem. We have a $10,000 deposit made into an account that pays 4% interest compounded annually. Find an equation that models the situation and use it to predict how much will be in the account after 15 years. I'd like to start by just kind of looking in depth at what's going on for the first year. We know that we start with $10,000, and in the first year we're going to earn 4% interest. So the interest would be 4% of the $10,000, or 0.04 times 10,000, which is $400. Now, if we're going to want to figure out how much we actually end up with, we don't need to keep track of just the interest. We need to keep track of the total amount in the account. So the balance in the account is going to include what I started with, the $10,000, plus the $400 in interest, or $10,400. Mathematically, it would be nice to model this in a way that didn't involve two steps. So I want to think a little bit about what we really did here. Basically, we kept 100% of our original amount of money, 100% of the $10,000, and then we added an extra 4% of the $10,000. So in fact, what we really have is 100%, or 1.00, times our original 10,000, plus the 4%, or 0.04, times the 10,000. And if you think about factoring a little bit, if we were to factor out the 10,000, we've actually multiplied it by 1 plus 0.04, or 1.04. What's nice about that is instead of first calculating interest and then adding the original amount, we can actually do it all in one step. If I now had my 10,000 and multiplied by 1.04, there's that 10,400 at the end of the first year. That's a step that I can replicate from year to year. So let's go ahead and start creating a little table of values using this idea. I'm going to let T be the time in years, and I'm going to let B be the balance in the account in dollars. And my first time would be time 0, before any time has passed. When I first make that deposit, the balance would have been the 10,000. We figured out already, after 1 year, we had 10,400. And then by the end of the second year, will have earned interest not on 10,000, but on 10,400. So using this idea that I keep 100% plus an extra 4%, I can just take that 10,400 and multiply it by 1.04. And there's my balance at the end of 2 years. And I'll do one more. At the end of the 3rd year, I earn my interest on that balance. So again, I keep 100% plus I gain an extra 4%, multiplying by 1.04. I have a little over $11,248. Oops, 8. Goodness, can't write that number. 248.64. There we go. And of course, we could keep going if we want to. All right, let's think about modeling this with an exponential function. We've already seen that our multiplier is 1.04. That's exactly how we were getting each one of these. So that's going to give me the base of my exponential model. And we also have the y-intercept. When t is 0, b is 10,000. So there's the a value for the exponential model. And let's see, normally we would write y equals the a, which is 10,000, times the b, 1.04, to the t. Well, actually, I guess usually we write x. And my point was going to be that this time, the y value is the balance in the account, so we might want to write b, or even b of t, equals 10,000 times 1.04, and then our x values are actually times t. We've seen this in the past, where with a modeling equation, we usually like to use variables that have meaning in the problem. It helps us a lot later on when we try to plug things in. We know what we're plugging in for. All right, so let's just recap a little bit. In our model, the a value was that 10,000. And it actually represented the starting balance in the account, right? What happened at time 0. We're going to see that that's very common in our exponential models. The a is the starting value of whatever it is we're calculating. It's what happens at the beginning when the input variable is 0. B is the 1.04. And unraveling what that meant again, remember where we got it. The 1 represented 100%, getting to keep what we already had in the account. And the 0.0 represented the 4% increase. Typically, when we describe the meaning of the base in an exponential function, we're really focused on the increase, or if it's a decay, it'll be a decrease. We don't care so much about the 100% in our description. We kind of know that we keep that. So what I would usually say for this base, or for this to describe the effect of this base, is that it represents a 4% increase in balance each year. Again, we're going to find that this is very typical. When we're describing a base in an exponential modeling problem, we'll usually go ahead and think of our base as a percent, in this case 104%. We'll subtract off or get rid of the 100%, which was just what we started with, and then we'll focus on what's left as our increase, or if it turned out negative, as our decrease. That's summarized for you at the top of the next page. So again, A in our model represents our starting value, what happens when x is 0, and B is really our rate of change. To find it, we have to convert B to a percent, subtract off the 100%, which is just what you started with, and that will give you the rate of change, the percent rate of change per unit change in time, or whatever the independent variable represents. All right, let's try another one. We have a school district that has experienced a 6% annual growth rate since 2005. The district had 750 students in 2005. I'd like to write an equation for the number of students, S, in the district T years after 2005. I'm going to go ahead and create a table of values. You may not need it for this one, and if you don't, that's great. But I just want to make sure that we're really all following this well. So again, T is years after 2005. S is number of students in the district. All right, so let's see. We know in 2005 itself, which would be T equals 0, there were 750 students. That's going to be my y-intercept, my A value, and it is the starting value, given that we're starting our discussion in 2005. The annual growth rate is 6%, so after 1 year, I keep 100% and then I add another 6%, so I'm going to multiply by 1.06, and I have 795 students. After 2 years, again, I keep the 795, so that's 100%, plus an additional 6%, and I would round off to the nearest whole student, so I'm going to call that 843 students, and so forth. Clearly, my constant multiplier is that 1.06. The A again, the starting value when T is 0 is the 750. So, let's see here. Normally I would write y equals AB to the x. This time the y is actually S, the students. A is 750. B is 1.06. And the x value were the times in years. If you take a look at that and think, gosh, I really could have written that down without ever drawing this entire chart, I'm sure you're right, and it's perfectly fine. In fact, I would encourage you to do so. In an exponential function, if you know the beginning value, 750 students at the beginning time of 2005. You can just put that right in there for your A. And if you know the growth rate, we simply have to go back and say, yeah, we got 100%, we keep everything we had, plus we add the 6%, and then convert to a decimal, and there's your B. So, not absolutely necessary to draw the table, although you can if it helps you. If you can identify the pieces right from the problem, that's okay too. All right, so let's talk about the A and the B. Again, the A was 750. And just like when you were interpreting M and B, the slope and the y-intercept for a linear function, and I asked you to be very specific, give it in the context of the problem, I'm going to ask the same thing here. Use specific language, not general language. Make it a sentence that someone could understand even if they had never read any of the rest of the problem. So here I'm going to say, in 2005, which is the T equals 0, there were 750 students. Okay. That sentence makes sense even if we never looked at any other part of the problem. The B is the 1.06. Again, working backwards, that's 106%. Take off the 100%, which is just what we started with, and that shows us that we have a 6% growth. So as far as interpreting the B, I would want to write essentially what they said here, which is the number of students increases by 6% per year, or annually is fine. Okay. And I know that information was basically given in the problem this time, but I wanted you to see how that relates back to what we were told. We won't always get told that much, so sometimes we'll have to come up with this a lot more on our own. All right, finally, I'd like to know how many students were in the district in 2011 based on our model. So 2011, let's see, since we started in 2005, that would be 6 years later. So t equals 6. And we'll just plug into our exponential function, s of 6. And again, rounding off to the nearest whole student, we're looking at 1,064 students. All right, we'll pause there and do a couple more examples in the next video.